In this lesson video, we're going to start Unit 6 with Day 6.1. We are going to jump right into some vocabulary here. We're talking about circles in Unit 6. Now, this video might go kind of quickly through some of the vocab. You can see I've already filled in some of this. If at any point you need to pause the video to copy things down, go ahead and do that. But make sure you're kind of following along, and I'll try and outline things and point to them whenever I'm talking about different things. So the first thing we want to talk about are circles, and we want to learn some new verbiage and vocab words when we talk about circles. Some of this might be a review for you, but some of it might be pretty new. A circle is just a round shape that has a total of 360 degrees. Okay, so we're going to use that quite often. We'll use that 360 to help do other measurements and find other measurements. Also, every circle has a point called the center. A center is the point in the middle of a circle, and the circle is named using the letter of that point. And so what we can do is, if I gave you this picture and I marked the center of that circle A, I would call that circle A, or we can use the symbol for a circle instead of the word circle, and that's just a circle with a dot in the middle. So that would be read as circle A also. Okay, every center has a radius too. A radius is how we measure the size of the circle. All right, a radius is a segment from the center of a circle, segment from the center of the circle to the outside edge of the circle. It is exactly halfway across the circle. It looks like this. From the center to a point on the circle, that's the radius. Every circle also has a diameter. A diameter is a segment that has endpoints on the outside edge of the circle and goes through the center, and it's all the way across the circle. So that would be a diameter, from one side to the other through the center. Now, those might be the only terms that you recognize so far, and that's okay. If we move forward, we're going to talk about some other segments. One of those is called a chord. The word chord means a segment in which both endpoints, which are defined by letters, lie on the outside edge of the circle. So if I've got a circle here, and I put a point here and connect it over here to point over there, we'll call this one A, this one B. That is a chord. Okay, we would call that segment AB a chord. Now, when I do that, when I put 2 points on a circle, it actually also creates something called an arc. An arc is a portion of the outside of a circle or a portion of the circumference of the circle, and it's shown with this arc symbol. So if I gave a circle here, and I put those points A and B there, this portion of the outside edge of the circle, this curve, is called an arc. An arc is measured in degrees. It's a portion of the full 360 of those degrees. And every arc can be classified as either a semicircle, minor arc, or major arc. So let's look at these one at a time. A semicircle is an arc with endpoints on the diameter. It is exactly half of the circle, or 180 degrees, and it is named using 3 letters. So I've given you this example. Arc ABC would be considered a semicircle, and it would look something like this. If I call this circle E and put point A here, point B on the other side of that diameter, I'm sorry, not point B, point C. Let me make it match. Okay, point C has to be the other one. B would be somewhere else along that semicircle. So arc ABC is a semicircle. It's half of the circle. And you have to use 3 letters. That's if it measures exactly 180 degrees. But if an arc is less than a semicircle, okay, or less than 180 degrees, we would call that a minor arc. Now, minor arcs only need 2 letters to be identified. So here on the same kind of picture, on circle E, we've got the diameter AC, and I put point B up here. This arc from A to B, not the full semicircle, not half of the circle all the way to C, but just from A to B would be considered a minor arc. It's less than 180 degrees. Well, if I have an arc that is greater than 180 degrees, or greater than the semicircle, it's called a major arc. And a major arc is named using 3 letters, such as ACB. And I'll show you that same picture, but I'll show you what I mean by arc ACB. I'm going to draw the same diameter with E as the center of my circle. So the diameter would be AC, and I'm going to put B up here, kind of the same place. ACB starts at A and goes all the way around to B the long way, not the short way. Okay, goes all the way to B beyond half the circle, so that's why I use this other point C in the middle here to show that I'm going the long way from A to B, not the short way. And those are arcs. And we'll get back to those later on in the lesson. So there are 3 more vocab terms, actually 2 more. We've already talked about what a chord is. I'm just rewriting this definition. It's the same thing as on the previous page. A chord, remember, is a segment where I have endpoints on the circle. Okay, this would be a chord here, stretching that segment through there. What I want you to notice about a chord is that the endpoints are on the circle, but the rest of the chord is inside the circle only. Okay? So in a chord, it's a segment in which both endpoints, defined by letters, lie on the outside edge of the circle. All of a chord is inside the circle only. Now, this next word, tangent, you might recognize from our last unit when we talked about sine, cosine, and tangent. This is not the same word, tangent, or it's not the same kind of thing. It's the same word, but just a different meaning of the word, different use of it. A tangent is a line or segment outside of the circle that touches the circle at exactly one point, and it never extends inside the circle. So all the points of a tangent are outside only, except for that one place that it touches or intersects the circle. We'll look at some examples from in our next portion of the notes, but I want to make sure you get these terms written down. And finally, our last vocab term here is the word secant. This is pronounced secant. A secant is a line that intersects the circle at 2 points. So it might look like this, where it goes through the circle at 2 points. It is both inside and outside the circle. Okay? So what we want to do here is we want to use our vocabulary terms and name each of these given parts of the circle using those words. So we'll kind of go through this together. First one, LQ. You'll notice this is segment LQ. This symbol means segment. So LQ down here starts at L, goes to Q. It exists only on the outside of this circle. It touches the circle at point Q, but that's the only one place it touches. Well, since it's a segment outside of our circle that touches at exactly one point, this is a tangent. Okay? Point P. Point P is at the very middle of this circle. That makes it the center of that circle. Segment WY. WY over here on the right goes from W to Y. Endpoints are on the circle. It is inside only. That makes it a chord. Now, UY, this is actually a typo. Please make sure you make this change. UY has arrows at both ends, and if you look at the picture, that makes sense. UY is a line that goes all the way through the circle, but it is inside and outside and intersects the circle at those 2 places. That makes UY a secant. Okay? RY. R starts here and goes through Y. R and Y, those endpoints are on both, they're both on the circle, but it goes through the center of this circle X, which makes this a diameter. It goes all the way across the circle through the center. Part F, PN. PN is this one, this segment from P to N. That's only half of the full width of the circle. It starts at the center and goes to a point on the edge. That makes this a radius. Okay, for part G, this is a vocab term that we didn't actually write down, so I'm going to teach it to you as we do this. Angle RQN. We haven't talked about angles yet, but I'm going to trace this for you. Angle RQN. RQ is a chord, QN is a diameter. When I connect those and form this angle, the vertex of that angle is at point Q on the circle. And I want you to write this down. Vertex on the circle. When the vertex of an angle is on the circle, or the vertex of any shape is on the circle, we refer to that as being inscribed. So since the vertex of this angle is on the circle, we call this an inscribed angle. So angle RQN is an inscribed angle. It's all about where the vertex is. Okay? Now let's take a look at these last three on the top right. Now we are talking about an arc. Arc MQ. There's two letters. You should remember that two letters means it has to be a minor arc. But you can also see on the picture from M to Q, the two letters tells me I'm going to kind of go the short way. That would be a minor arc then. The next one, since I'm going in order, I here is another angle. There's another kind of angle. This one's not an inscribed angle, and I'll show you why. UXY, if I trace that, UXY puts the vertex of that angle at point X. That vertex is at the center of this circle. Since the vertex is at the center, we call any vertex or any angle where the vertex is at the center of a circle, we call that a central angle. So UXY is a central angle. Another central angle might be MPQ. Okay, that would be a central angle. All right, finally, one more arc to talk about, arc RWU. Arc RWU, we start at R, we go through W to get to U. So we're going the long way around the circle. Even though we kind of skip over the Y, we don't need that letter. We're going from R to W and then on around to U in that direction. That's what tells me this is a major arc, because I go more than half the circle. Okay, so that's how we can identify these different vocab terms. This part of the notes we actually kind of skipped over. I'm not going to ask you to draw your own yet. We're going to go ahead and jump ahead to the next portion of our lesson. We're going to talk about area and circumference in this lesson. All right, as we talk about area and circumference, there are some formulas we need to use, and so it's very important that you write down what I write down when it comes to talking about formulas. When we talk about the area of a circle, there's all kinds of different area formulas for different shapes, but for circles, the area formula is A equals pi r squared. And that will give us the amount of flat space taken up by a circle, and that is in square units. And this r here means the radius of the circle. So whatever the radius is, we square that, or take it times itself, and multiply by pi. Remember, pi is approximately 3.14, but we're not going to use the estimation of 3.14 in our calculations. We're going to find the pi button on the calculator, and I'm going to walk you through how to do that on my on-screen calculator. That's how we're going to find the area. But we also have a formula for circumference. Circumference is like the perimeter of a circle, but because it's a round shape, we call it the circumference. The distance around the edge of the circle is what circumference is, and there's two different formulas I could use. The first one uses the radius. So the circumference of a circle could be found by taking 2 times pi times the radius. The other formula, other way of thinking about this, is to use the diameter. The circumference is also pi times the diameter. So r again means radius, and d means diameter. And so we can find circumference that way. Since we're talking about radius and diameter, it's kind of important to pay attention to that connection between those two, or the relationship between those. So if I were to draw the center of this circle and mark a radius, and then go in the exact opposite direction with another radius in a straight line, that total segment is a diameter. Well, you can see it takes 2 of those radius to equal the diameter. So the radius is half of the diameter, and you can also think of the diameter as twice the radius. Or if I were to write this out in an equation, the radius equals half of the diameter, or the diameter is 2 times the radius. Okay? So if I have a radius of 2, the diameter would be twice that, 4. If I have a diameter of 4 pi, the radius is half of that, we would call that 2 pi. If the radius of a circle is 2.5 pi, I would double that or multiply by 2 to get the diameter, which would make it 5 pi. And if the diameter of a circle was 30, half of that would be the radius equal to 15. So we need to use that connection between radius and diameter sometimes. So the first thing we're going to do here is start working through, and I'm going to give you a measurement and ask you to find another measurement. Okay? So we're going to start pretty simple. I'm going to give you a radius and ask you to find the area for number 1. Now we're going to write answers 2 ways on some of these. We're going to write answers in terms of pi and rounded to the nearest tenth. So we'll have an exact answer first in terms of pi and a rounded answer next. And it's going to be, the answer is really going to be equal. They're going to be equal to each other. But I need to describe what this phrase in terms of pi means when we get there. So let's go back and just talk about the formula first. If we're given the radius equal to 13 of some circle, the area would be found by taking that pi times r squared amount. So that's our formula. We always want to start by writing the formula. And then we plug in what we know. I know r is 13. So I come down here and I write this again. A equals pi, but instead of r squared, I write it as 13 squared. And I can put my dot for times even if I want. Now, to write our answer in exact form in terms of pi just means to do all the calculations except for multiplying by pi. Well, that means all I can do is that part to start with. 13 squared, 13 to the second power, is 169. And because I still have a pi in front, I'm actually going to write times pi at the end by just putting the pi. That means 169 times pi. But that is my exact answer. 169 pi is as exact as I can make that without rounding for that value of pi. Then to write my rounded answer, I just finish the calculation. I do 169 times pi in the calculator. So I'm going to bring up my calculator on screen. Let me get it moved over to the other side. There we go. Okay, zoom in here if you need to, but we are looking at 169 times pi. So if I do 169 times pi, on these calculators, it is right above this little exponent key. So it's the key right above the division sign, but I have to hit my second option to get pi to show up. I don't want to use 3.14. I want to use the actual value for pi programmed in my calculator. So when I do 169 times pi, I get something that would round to 530.9. Okay? So that's how you write an exact answer and a rounded answer. Okay, on number 2, we're going to do the same kind of thing, but we're using the diameter to find the circumference. So since I want the circumference this time, I want the circumference formula, and since I'm given a diameter, I want the circumference formula that uses diameter with the d. So the formula I'm going to write down is c equals pi times diameter. I know d is 20, so I just replace that. Pi times 20, that already is my exact form answer. I just have to flip it around. I always write the number first, then I write my pi symbol last. So my exact answer is 20 pi. But to get the rounded answer, I need to actually do that in my calculator. I need to do 20 times pi. And I get 62.8. Now, for the sake of time in this video, I'm going kind of quickly, so if you need to pause it all to copy things down, go ahead and do that. Otherwise, we're going to move forward. For number 3, we're working a little bit differently here. For number 3, we are given an area, and we're going to work backwards to find the radius. So the first thing we do is we write our formula. A equals pi r squared is your area formula. But now I'm going to replace A with this total 132. And now I'm going to solve this for r. Well, to work backwards and solve for r, the first thing you do is divide by pi. Canceling it there, but I have to do that calculation before I can do anything else. So I'm going to do 132 divided by pi, and I get about 42.02, we'll call it. That is equal to r squared, but that's not my radius. That's the radius squared. I still have to cancel out the square, so I'm going to take the square root of both of those. So the square root of 42.02 is about 6.5. So my radius would be about 6.5, 6.5. Okay? Let's try another one. Same thing here on number 4. I'm giving you a total measurement this time. I'm giving you the circumference measurement, and I want to find the diameter. So again, I want to use the circumference formula that uses diameter. C equals pi d. But instead of plugging in a diameter and getting circumference, I'm going to plug in a circumference to find the diameter. So we divide by pi, and my diameter is equal to 38.5. Okay? Now, we can take these one step further, where I give you a certain area, and I work backwards to find radius, and then I use that again to find the other measurement, circumference. So it's kind of like I'm starting this way. I'm going to start with the area. I'm going to work through that formula to equal the radius, figure out what the radius is. Then I take that radius, and I use it to figure out what the circumference is. So these two blanks are not going to be like the exact and rounded answers here. They're just going to be, one is the radius, and then the other one here is my circumference. So let's start with the area formula. Area equals pi r squared. I'm going to take this 32.23 and plug it in for A. So 32.23 equals pi r squared. To solve for r, we divide by pi, kind of like we did on number 3 above. 32.23 divided by pi is about 10.26. But that is equal to r squared. I need to still do the square root to get r by itself. So if I do the square root of 10.26, I get that the radius is 3.2. So that's the first answer I want to write down. 3.2 is my radius. I want to use that radius of the circle now to find my circumference. The formula for circumference of a circle that uses radius is C equals 2 pi r. So I'm going to plug in 3.2 for r here. 2 pi times 3.2. And I can do that calculation kind of all together in the calculator. 2 times pi times 3.2. And I get a circumference of 20.1. Okay. Now, for the sake of time in this video, we're going to skip number 6. It uses kind of the same logic, but we start the other direction. We start with the circumference, we work backwards to the radius, take that radius and find the area. So the in-class notes document that is attached to the homework check has this filled out completely, and you can check these answers of anything we skip. But for the sake of the video, we're going to move on to the next big idea. And that's the idea of arc length and sector area. So we've talked about what arcs are. Anytime I put an arc on a circle, I take 2 points on the circle and I kind of represent that part of the curve. That arc has a measure in degrees, but it also has a measurable length. So if I call this point A and this point B, and the center of my circle, let's call it E again. From E to B is a radius of the circle. But from E to A is also a radius. This angle created here, we're going to call it x degrees. That is equal to the degree measurement of arc AB, but there's a length that goes with that, which would be a part of, or a portion of, the circumference of a circle. So the measurement of an intercepted arc, we use the word intercepted arc because it is intercepted by a radius here and a radius here, or intercepted by this angle at E, the central angle. It's a part of the circle's total circumference. Well, that also creates this idea of this section, whenever I kind of put this boundary in with one radius, the other radius, and then the arc, that region has an area that we can measure, and that would be a portion of the circle's total area. And that's the amount of square space taken up in that sector. We call that a sector. Arc length is going to be represented by the variable capital L. We're going to use capital L to refer to arc length. And sector area we're going to refer to as capital S. So this is how we're going to calculate sector area and arc length. If we're trying to find arc length, if we're trying to find the arc length, the length of an arc, we're going to use the left side of this proportion. We're going to use the left side. Okay? Where arc length, L, over the total circumference 2 pi r has to equal the central angle measure, we'll just call that x, over 360. I'm going to write that over here as its own little formula. Arc length L over the full circumference, we're going to call that 2 pi r. That's how we find circumference. Has to always equal x, the angle measure, out of a full 360. Because the full circle is 360 degrees. That angle we're using is only x degrees, however many degrees we're told to use. But if we are looking for the area of a sector or sector area, we're going to be using the right side. We're still using kind of that middle portion, that where they overlap, but we're using that part of the proportion to find our sector area. So again, I'm going to write a more simplified version of just that right side. Okay, our sector area out of the full area, pi r squared, has to equal x out of 360 as well. Okay? So, for each of these questions, we are going to give our answer. We're actually only going to give a rounded version of this answer. Okay, we're not going to give a exact answer in terms of pi. But on a lot of these problems, sometimes I just give you the words, but a lot of times I will still give you the picture. So if I've got circle A, mark the center A, with a radius of 14 and a central angle of 132 degrees, I'm going to take another radius and make that 132 degree angle. It doesn't have to be exact, but you should recognize 132, that's more than 90. It's bigger than 90. It's an obtuse angle, but it's still less than 180. I should be able to find the length of the intercepted arc, or arc length, from here to here. And arc length, remember, is that capital L. So I'm using this formula. L over 2 pi r has to equal x over 360. And I'm just going to plug in what I have. So I've got a radius of 14. So that goes into the 2 pi r. I still have my L for arc length, but instead of 2 pi r, I'm going to do 2 pi times 14. You can use the parentheses for that, or you can just do times 14 like that. That has to equal this angle measure, 132, out of 360. Okay? So as we kind of progress forward, to solve this proportion, remember, you cross multiply. That gives me 360 times L equals 132 times 2 pi times 14. To get L by itself here, we're going to divide by that 360 to cancel it. Notice I haven't really done any decimal calculations yet. I'm kind of saving all of that up to put in the calculator at one time. So I can do all of that in the calculator like this. I can do 132 times 2 times pi times the 14, that's the whole top part there, and then just divide by 360 at the end, and I get about 32.3 for that length of that arc. Okay? So we can find the area of a sector kind of the same way. Again, if we're going a little fast, just pause the video and copy things down. But if I mark the center here and I draw a radius again, this circle has a radius of 22 inches. And they want the area of a sector when there's a central angle of 51 degrees. 51, that's less than 90, so we'll just call that 51. So there's my arc, but it creates this sector right there. And I can find the area of that by using this formula. S out of pi r squared has to equal x out of 360, where x is 51, and I already know r is 22. So I'm going to fill that in. S over pi times 22 squared equals 51 over 360. And we cross multiply again, giving me 360 times s for that side. That has to equal 51 times pi times 22 squared. Again, divide by your 360 to cancel that. And so that's what I put in the calculator. 51 times pi times 22 squared divided by 360, we should get 215.4. Okay? As we keep moving forward then, a lot to throw in this first lesson, I understand, just kind of hang with me. We can do the same idea with these kind of problems, but I'm going to show you kind of the shorter, easier way to do these. We're given a regular polygon inscribed in a circle. Now, regular means all sides are equal, and inscribed means each vertex is on the circle. And they tell you the radius of this circle is 18 for both problems. R equals 18. Now, they want to know the length of an arc, AB, where A and B are consecutive vertices. So consecutive vertices just means right next to each other along the polygon. So in a triangle, any two would have to be consecutive, so I'm going to call one of them A, one of them B. They want that arc length. But I didn't give you a central angle to use here, but there is an easier way to think about this. The length from one point like A all the way around the circle would be the circumference. And circumference is equal to 2 pi r. So even though I don't know a lot of other information, I could find the total circumference. But since each side of this triangle is congruent, each of these three arcs on the outside have to be congruent as well. So AB is the same as these other two. Well, that means there are three equal arcs that make up the entire circumference. So the arc length is equal to that total circumference divided by how many sides that polygon has. In this case, 3. So all I have to do is 2 pi times the radius of 18 and divide that by 3. So when I do 2 pi times 18 divided by 3, I get 37.7 for that length of that arc. Instead of using an angle measure to find out how much of the circle I'm using, I'm going to use the number of sides of the polygon. Let's try that again for number 10. This time there are 1, 2, 3, 4, 5 congruent sides. If I want the length of an arc between two consecutive vertices, A and B, remember circumference is 2 pi r, so my arc length is that 2 pi r divided by 5 sides, which would be 2 pi, I know my radius is still 18, 2 pi times 18 divided by 5. So this time, my arc length is 22.6. Okay? All right, we are getting real close to done. We've just got a couple examples left, so let's finish these up. All right, to find the radius given that the arc length formed by a central angle is approximately 5.76 centimeters and the sector formed has an area of approximately 15.84 centimeters, here's what we're going to do. I'm going to give you a shortcut. If I go back and look here, I know that arc length out of circumference is equal to angle measure over 360, but so is sector area out of the full area. So these two are actually equal to each other. So that's what I'm going to start with. I know that arc length out of 2 pi r has to equal the same thing as sector area out of pi r squared. I can manipulate this formula to solve it for r, and when I do, I get this. And I just want you to make sure you copy this down. If you want to come by and go back over this with me, I can gladly show you where I'm getting this. But if I solve this equation for r, if I get r by itself in this equation when I cross multiply, the pi on both sides cancel. The radius is actually just the sector area times 2 divided by the arc length. That formula is going to help me with this problem because I'm giving you the arc length, 5.76, and the sector area, 15.84. Well, I can plug those in for S and L here. The S is 15.84. I'm going to multiply that by 2 and divide by the arc length, 5.76. So when I do that, I get my radius of 5.5. Again, I'll show you that over here on the calculator. 15.84 times 2 divided by 5.76 is just a simple 5.5. Okay? Same idea on 12. I've given you an arc length of 7.54 and a sector area of 27.14. So again, I'm using the radius formula that radius equals sector area times 2 over arc length. So I'm going to do sector area, 27.14 times 2, divided by arc length, 7.54. So 27.14 times 2, divided by 7.54. And we get a radius of about 7.2. So we went through that pretty quickly. If you have more questions, please go ahead and come on in, ask me for help, send me a message in Canvas. I'll work through this with you. But that completes our first lesson of Unit 6, Day 6.1.